Hello again. In this video I'm going to be doing a deeper dive into the ZVS Tesla coil. This is being directly driven. And here I'm showing the tap points that I use on my existing ZVS Tesla coil. It's important to have a good connection. This one I made by hand out of aluminum. If you would like to see a video on this, I can do that. Just let me know. And it's really important to have a good connection because you don't want your terminals connections to be heating up. It's good to use an alligator clip at the beginning until you find your tap point, and then once you do, then you want a solid connection to keep everything nice and cool. I was showing a little bit of how I did this coil. There's different ways you can do tap points as long as you have a good connection. This was my homemade ZVS that I did. I have another video where I go into some details on how to build that. And then here I have a switch that actually changes the frequency to run the coil with different types of breakouts, or depending on what I'm wanting to do. It can increase power. This video I'm going to be showing how to tune a Tesla coil run by a ZVS. They can be a little tedious. And this is the new ZVS little driver deal I made. And I'm running this cap right here, this single 150 nanofarad. This is a Cornell cap. You can find them on Mauser and DigiKey and a few other product places. They work really well. And showing how I wired this here, I'm not using any Zehners. The resistor I have here is a 10K resistor. Then it has a few diodes, but I'm running the gates on its own, so you don't have to worry about the hard starting of the ZVS. It's better to run the gates. These are the diodes that help with the switching, and I actually ran little jumpers here to where they could be wired without having to extend them or anything to keep these heat sinks apart. They're thermo pasted right directly to the heat sinks. They're isolated, so you don't have to worry about them having pads, which is better for dissipating heat. You can see I'm pointing out how exactly I wired it. I have a schematic in my other video. I can share it here. These are 100 ohm resistors that I'm running just for the gates. They're on their own separate supply, which is typically 12 to 15 volts. And it will start it to oscillate. And you can see you have to have the grounds tied into each other from the main power supply and the separate 12 volt supply. And this is where I plug in the gates basically with a separate power supply. This is the 12 volt supply that I'm using, and this is the main supply that's powering the main supply of the ZVS, and it's capable of putting out about 51 volts with 10 amps at its maximum power. You typically want to have your caps as close to the primary as possible, but I'm just showing in this demonstration that it will still work even though everything ain't as it should be. Like the primary I have here, it is just kind of thrown together, just kind of makeshift deal to show you that it's not real critical, but every little bit counts when you're trying to get the maximum power out of these. You want to have a tighter primary, you know, probably about a 1/4 inch away from the secondary is about where you want to be. And you always make sure you ground your secondary. That's very important, that you have a good earth ground to your secondary. And that's what that goes to right there, is to a ground rod that's actually in the earth. You can get by with other ways, but this is the way I typically like to do it. And I have an oscilloscope hooked up. That is a real handy tool. It can get you dialed in a lot faster than just trying to mess around without an oscilloscope. But for this demonstration, I wanted to show so you can see the differences and what you're doing and how it can assist and show you what's going on. So I'm plugging in the gates now. So as you can see on the scope back there, it's resonating right now without no main power, just gate power. And you can see the light ain't lit up, but as I bring my hand closer, it lights it up, but doesn't maintain the lightness on its own, which is saying that it's not in its optimal resonance. And here I'm going to change it to a different tap point, just one turn, and you can see now that it's resonating on its own by lighting the light on its own. And I'll change the tap point again, and you can see how I bring my hand close to it and it's lighting it. And you can see here the frequency is 206 kilohertz roughly, and it won't light it on its own. Then if I bring it down a turn, you can see here where it's maintaining the light lit up, which means that it's close to its resonance. Still not perfect, but it's close. Now if I bring the tap point down another turn, the frequency will be a lot higher, and you can see how it's not resonating as high. It's having a hard time picking it up because it's not ringing the secondary very high, but it's right around 310 to 320 kilohertz, and it won't light the light at all. And while I'm doing this, I've never killed the 12 volt power source to the gates. And you can see here that now it's resonating back to where it was around 340 kilohertz. And then now the light's lighted and it's holding on there. When you bring your hand closer to it, it does change the resonant frequency of the coil, which is causing it to tickle the light. The light indicator really helps to know if the secondary is wanting to resonate. Now I'm actually feeding the supply voltage. I'm turning it up right now, and you can see now it's starting to promote a little bit of breakout. It's still not in its ideal tune, but it's close. The ZVS coils, they're really kind of funny, and you have to play around with the tune quite a bit. What's nice about this supply here is that it actually tells you the amperage that it's drawing to as you're turning it up. So you can see with this current tune, with a little bit of promotion of output, it's at 240 kilohertz. So now it's just on gate voltage again. This is reading a little bit of voltage because it kind of backfeeds just a little bit into the supply, but it's really no voltage at all that the supply is giving it at the moment. So here I grabbed a smaller secondary, smaller diameter. It's not nearly as good of coupling. And I'm just gonna leave, everything's the same. I'm just gonna see if I can't get this coil to resonate. You can see that the gates are resonating and I can't get the light to light, but just barely. Now I'm going to show that you can add some voltage to it and you can actually get the light to light, but it's not in near resonance. Still light to light, but it's not in its ideal tune. I'm showing this just to give you an example of when you're not in resonance, not just to keep putting power to this system, because you can blow it if you go too high a voltage. As long as you stay under 60 volts DC, you're typically okay. But sometimes you can get amps where they'll run away from you because it's not in resonance, or the frequency will be way too high, and it's hard to know that if you don't have an oscilloscope. Okay, on to another secondary. This is another secondary. It's wound with 30 gauge. This is a 3-inch form. And I'm going to see if I can't get it to work with everything left the same. So just gate power. And you can see how this one already off the gate is lighting the light. So this coil may actually put out a little output, even though it's the same diameter as the last one I just ran. But the last one I just ran, the resonant frequency was a bit off on to get it to work with this system. Also, not much coupling on the secondary versus the primary. The distance is pretty far. So now I changed the tap point to see if it would work at all, and you can see how just by changing it one turn makes a big difference in its resonance. Now it's working. And now I'm just changing the position on that same turn that I was at, which can make a difference, believe it or not. A quarter of a turn at a time, or even less, can make all the difference on getting output versus not. And you can see it's hot now, and it's putting out output. Ain't a whole lot, but it is working. And here I'm showing how the resonant frequency can change from one point to the other. Like when you go from one side where you're tapped at to the other side, it can totally change the frequency, which is kind of odd, but the ZVS's do that. You can see I'm just a little bit slightly different tune, but it's changed the resonant frequency by almost 40 kilohertz. And this is where I was, right here. And all I did was move it just that much, and it changed it from 30 to 40 kilohertz. So typically when you're trying to tune this, you gotta keep it going the same direction on the same side. If you flip the wire, it kind of adds to the turn or takes away from the turn. So when you're tuning and you're getting it close, you have to keep that in mind. And I'm just showing how the more turns you add, the lower the frequency goes on the primary. The less turns, the higher the frequency goes. This is only gate power still, but I'm showing how at this resonant frequency it doesn't want to maintain the light on, which means it's not ideal. And now I'm adding power to it just to see if it will put off a little bit of output, even though it wasn't ideal frequency and it didn't. So, but then I move it one turn down, and after exciting it, it should be able to maintain it with just the gate power, which it is. It's not ideal, but it's still working. So it should put off a little bit of output. If I turn the voltage up here, yep, there it is. You can see just a little bit. And I'm going to show you here how when you bring your hand closer to it, it can change the resonant frequency and cause it to put out a little bit more output. Objects around a Tesla coil and all that kind of stuff can affect resonant frequency. And if you watch the scope behind, you can see that. As I bring my hand closer, it's changing the resonant frequency of the secondary because it's coupling with my hand. So I got the first secondary back on there, which is the way I made this primary to fit mainly, which it could be better, but just for demonstrations. I'm going to give it one more run to show the output, and then I'm going to take AC and then halfway rectify it and show how you can get an increase on your overall output length, and it requires a little bit less power and it doesn't heat up things quite as much. Gives you sword looking arcs. And as you can see, this is just gates only right now, and it's tickling the light on its own. And now I'm increasing the power. Another thing I forgot to mention was you want a sharp breakout, and you typically don't want to use a top load. And if you do, you want something very small because it adds pressure to the system. It takes away from it being able to break out. And here I'm showing the components, the type of components I use. The diodes that I'm running down there, which is the FR307s. That's are what's helping the gates switch back and forth. And you can also use these, which are the UF4007s. I like using the 307s because they have a little bit more higher amp rating, but these will work too. And these are the type of switches I'm using. They're 260Ms, and you can get these from DigiKey, as you can see on there, or Mauser, and they work really well. They're rated for 200 volts and 50 amps. But on this circuit, you don't really want to go over 60 volts. This is the power supply that I was using. That's good for about 52 volts and 10 amps. It works really well, and it's adjustable, which I really like. So now I have the half-wave rectified setup here. There's two diodes, single diodes, and one's for the ground and one's for the positive. and I'm using a step down transformer. These are the diodes. They're 60 amps, 300 volts, and they work really well. Probably don't need them quite as big as those, but I'm taking 120 and stepping it down to about 60 volts, and then using a variac to control the voltage, so it's adjustable. Still using the separate power supply to turn on the gates, and you can see where the scope just picked up the oscillation, and you can see how it lights up the light and it stays lit without having to stay holding it or anything. And now I'm going to give it a shot and show you how this works out, and I'm also going to tune it to where it works a lot better. So this is full voltage here. Now I'm going to show you how critical tuning is and how much performance you can get by progressing the tune and getting it to work at its most efficient tap point. And you can really take some time, and it's always good to take time to get this tuned the best you can. And if I had everything a little bit more tuned, as in primary, wire lengths, cap being closer to the primary being closer to the secondary, this would all help efficiency. And you can see me rotating the primary. It's because I didn't want to take the tap and go around the other way, because it can cause the tune to act weird. So I'm continuing to go the same route that I'm going. Tuning really is everything on these coils. I'm hoping this is helping understanding of these ZVS coils. And you can see how much of a difference tuning makes. It's progressively getting better. And I'm going to tune a few more times here. So this is about where I ended up with this, makeshift system. And I'm going to show you how well the gates actually work now with just gate power, with no source power, and how well it lights up this light, and how you can get a little bit farther away from it. figured I'd show you all how to do a do-it-yourself tap point for the primary to get a good connection. And I hope this video was helpful. And y'all have a good one. Thank you.